Hi, my name is Michael Pendazis, and this is Math 231 Linear Algebra, online lesson number 11. In this lesson, we will cover chapters 7 and 8, and we will finish the material for the course. Okay? Last lesson, we covered 5.3 complex vector spaces, 6.1 inner products, 6.2 angle and orthogonality in inner product spaces, and 6.3 the Gram-Schmidt process. And in this lesson, we will cover 7.1 orthogonal matrices, 7.2 orthogonal diagonalization, 8.1 general linear transformations, 8.2 compositions and inverse transformations, and 8.3 isomorphisms. Okay, so let's get started. So 7.1 is orthogonal matrices. Okay, and so we're going to start off with the definition of an orthogonal matrix. So the definition is a square matrix A, which I'm going to abbreviate as a square A, is orthogonal as a matrix if its transpose is the same as its inverse. Or that A transpose is equal to A inverse. Or, equivalently, A transpose is equal to A transpose A, which is equal to I. And we'll label that as the first point in this lesson. Okay? So definition, a square matrix A is orthogonal if its transpose is the same as its inverse, or A transpose equals A inverse, or A transpose equals A transpose A equals I, right? So here, the reason why this is equivalent to this is because A transpose being the inverse of A is equivalent to saying that A transpose is the matrix that you can left or right multiply by A and get the identity. Okay? Because that's the definition of an orthogonal matrix. Example 1 is an example of an orthogonal matrix. So for instance, this matrix A, which is 3/7, 2/7, 6/7, -6/7, 3/7, 2/7, 2/7, 6/7, and -3/7, that whole matrix is orthogonal since, I could write all the matrices out, but basically what happens is if you take the transpose of that matrix A, you take A transpose times A, you will get the 3x3 identity matrix. And so you can do the matrix multiplication, you could plug in what A transpose A is, multiply them, and you will get the 3x3 identity matrix. Okay, and so then that means that that this A is orthogonal by the definition, by definition of an orthogonal matrix right there. Okay, so that's the start. Let's keep going. The next thing, we should talk about is theorem 7.1.1 in this section, which is the following are equivalents for an n by n matrix A. Right? TFAE is the abbreviation for the following are equivalent. So the following are equivalent for an n by n matrix A. Statement A, capital A is orthogonal. Okay, that statement is true or false, not both. B, the row vectors of A, form an orthonormal set in Rn with the Euclidean inner product. Okay, so the row vectors of A form an orthonormal set in Rn n space with the Euclidean inner product. That's statement B. So that means that you have an n-band square matrix A, and so if you take the rows of A, you can make them row vectors. Those row vectors form an orthonormal set, right? Remember what that means is that that's a set that's orthogonal. If you take any two row vectors, the inner product between them is 0. Their lengths are 1, and so they form an orthonormal set. All right. And when you say that they're orthogonal because the inner product of any two rows is 0, you're using the Euclidean inner product, right? The Euclidean inner product is the one that says the inner product of V, U, and V as vectors in Rn is U1, V1 plus U2, V2 plus dot 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 plus UN, Vn. That's the Euclidean inner product. It's the function that when you take two vectors in Rn and you take their inner product, we define that function that is equal to that. Okay? We could define it a different way. Every inner product satisfies the 4 properties of inner product, and so there's infinitely many inner product functions you can choose. But once you choose one, you now have that's your inner product function for your inner product space. Okay? So that's statement B, and statement C is the column vectors of A. Form an orthonormal set. In Rn with the Euclidean inner product. So this statement is basically the same as the other statement, except instead of using row vectors, we're using column vectors. So the column vectors of A form an orthonormal set in Rn with Euclidean inner product. Right? Okay, so the column vectors of A form a set that's orthogonal, and the length of each column vector is 1, and using the Euclidean inner product, that inner product there. Okay, so that's theorem 7.1.1. It says that statement A, that statement B, and that statement C are all equivalent. They all have the same truth value. So if one statement is true, all 3 are true. If one statement is false, all 3 are false. That's theorem 7.1.1. Theorem 7.1. Theorem 7.1.2. A, the transpose of an orthogonal matrix is orthogonal. Okay, so the transpose of an orthogonal matrix is orthogonal. Okay, right, again, the definition of orthogonal matrix is the transpose of that matrix is equal to its inverse. So if you have a matrix with that property, transpose equal to its inverse. That matrix, now if you take the transpose of that orthogonal matrix, the transpose of it is orthogonal. The transpose of that orthogonal matrix is a matrix whose transpose is equal to its inverse. Okay? B, the inverse of an orthogonal matrix is orthogonal. Okay, so the inverse of an orthogonal matrix is orthogonal. Okay, so if you have an orthogonal matrix and you take its inverse, that inverse is also an orthogonal matrix. That's statement B. Statement C. These statements are just each true on their own. This is not saying they're all equivalent like the last theorem. Statement C is a product of orthogonal matrices. Is orthogonal. Okay, so if you multiply a bunch of orthogonal matrices, the product, after you're done multiplying, the result is another orthogonal matrix. D, if A is orthogonal, then the term of A is equal to 1, or the determinant of A is equal to -1. Okay, so once you have an orthogonal matrix, its determinant is either plus or minus 1. It's either plus 1 or minus 1. Okay, and that's so that all 4 of those statements are theorem 7.1.2. Now theorem 7.1.3 is if A is an n by n matrix, if A is n by n, then the following are equivalent. Statement A is orthogonal. B, the norm of AX is equal to the norm of X for all X in n space. And statement C, AX dotted with AY is equal to X dotted with Y for all X and Y, in n space. For all n tuples X and Y. Okay, so that's theorem 7.1.3. Statements A, B, and C are all equivalent if A is an n by n matrix. Okay, so in statement A is orthogonal, right? So definition of an orthogonal matrix, you can know whether that's true or false, what that means. B, the norm of AX equals the norm of X for all X in Rn. If you take any n tuple X, its norm is equal to the norm of A times X. Okay, and then AX dot with AY is equal to X dot Y for all X, Y, and Rn, right? And the dot is the inner product. Okay, so that's theorem 7.1.3. And so these are two more theorems in this section. Okay, so let's keep going. Okay, definition. If A is orthogonal, if A is an orthogonal matrix, then T sub A, a function from Rn to Rn, which is multiplication, left multiplication by A. Left is understood by just the root multiplication. That's by convention. Multiplication is left multiplication, so left multiplication by A is an orthogonal operator on Rn. Okay, so this is the definition of an orthogonal operator on Rn. If A is an orthogonal matrix, then T sub A, the function T sub A from Rn to Rn, which is left multiplication by A, is an orthogonal operator on Rn. Okay, T sub A is the function left multiplication by A. So what that means, right, is that T sub A of X is equal to AX. That's a function that if you take a vector X in Rn, T sub A will map that X in Rn to T sub A of X, which equals to AX in Rn. Right? Okay, and that T sub A of X is left multiplied by A, so T sub A of X is equal to AX. That's an orthogonal operator on Rn. Okay, that's the definition of that. This is theorem 7.1.4. If S is an orthonormal basis, for an n-dimensional in a product space V, and if coordinates of U relative to S are equal to U1, U2, dot, 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 Un, and the coordinates of V relative to S is equal to V1, V2, Vn, then statement A is that the norm of U is equal to the square root of U1 squared plus U2 squared plus dot 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 plus UN squared. B is that the distance between U and V is equal to the square root of V1 minus V1 squared plus U2 minus V2 squared plus dot 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 plus U minus Vn squared. then C, the inner product between U and V, is equal to U1 V1 plus U2 V2 plus dot 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 plus UN Vn. Okay, so theorem 7.1.4. If capital S is an orthonormal basis for an n-dimensional inner product space V, and if the coordinates of U relative to S is that, and the coordinates of V relative to S is that, then A, the normal of U is this, the distance between U and V is that, and the inner product between U and V is that. Okay, so here for B, I wrote the differences. If you take each of the coordinates, the respective coordinates of the coordinates relative of U relative to S of U and V, right? So U1 minus V1 squared plus U2 minus V2 squared plus dot 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 plus UN minus Vn squared. And you take the square root of that sum. That's the distance between two vectors, okay? Okay, so that's just how you define the norm, distance, and the inner product in this situation. Okay, and so that's the theorem, theorem 7.1.4. Okay. If theorem 7.1.4 doesn't make sense, it's more because the earlier stuff doesn't make sense. If it doesn't make sense what the coordinates of a vector is relative to a basis, then this probably wouldn't make sense. If the stuff preceding that made sense, then that theorem would be very simple to understand. But the preceding stuff is a bit difficult, and that's what would make that harder to understand. Okay, theorem 7.1.5. Let V be a finite dimensional inner product space. If P is the transition matrix, from one orthonormal basis for V to another orthonormal basis for V, then P is an orthogonal matrix. Okay, so theorem 7.1.5. Let V be a finite dimensional inner product space. If P is a transition matrix from one orthonormal basis for V to another orthonormal basis for V, then P is an orthogonal matrix. Okay, so just going over some things, right? If V is a finite dimensional inner product space, right? That's like kind of like that sentence is a summary of a lot of things we've already done. An example of a finite dimensional inner product space would be R3, comma, plus, comma, standard scalar multiplication. So R3 would be the set of three tuples, plus would be the standard addition of three tuples. This would be normal scalar multiplication of three tuples. This would be a vector space, right? This would constitute a vector space, the team of these three things, the set and these two operations that satisfy the 10 axioms for vector space. So these three things and the 10 axioms hold, you have a vector space. Then, if you take that and you can join it with an inner product function, and in this case we could say the usual Euclidean inner product. Okay. So the Euclidean inner product is a function that satisfies the four axioms for conditions for an inner product function. So if all four of those conditions are satisfied for this function, when we add this function into our vector space, meaning these three things and the 10 axioms already hold, if in addition we have four axioms holding for this function, and we take the team of these four things, we now have an inner product space. So all four of these things combined, that team of those four things is in this case an inner product space. And then if we want to add to that, not just having an inner product space, we want to say it was finite dimensional, we would then say, if we went back to our original vector space here, and we looked at our vector space and said, well, what's the dimension of that vector space? We would find a basis for that vector space, and every basis has the same number of vectors. And so if we found a basis for that vector space, this doesn't matter, the inner product function here doesn't matter here, it's for this part of it. And then if we took those three things and found a basis for that vector space R3, if that basis had finite many vectors in it, then it would be a finite dimensional vector space. And then now with all four of these things is the finite dimensional inner product space. And so the statement let V be a finite dimensional inner product space says an enormous amount about what you're talking about. We have four things here, and all 10 axioms for vector space hold, all four conditions for an inner product function hold, you have a finite dimensional vector space here. All of that is what V is. So V is that, all of that. Okay, so we're going to assume we have something called capital V, which is a finite dimensional inner product space. So we are assuming a lot about the V we're thinking of here. Okay, so we're now assuming a lot about this object we're calling V. Okay, so all of that is in the first sentence. Now, okay, so V is our finite dimensional inner product space, which I'm saying all those things about that object V. If P is a transition matrix from one orthonormal basis for V to another orthonormal basis for V, then P is an orthogonal matrix. So what does that mean? Well, V is our finite dimensional inner product space. It's also a vector space. If we took one orthonormal basis, let's say B1 is an orthonormal basis, is one orthonormal basis for V. And then B2 was another orthonormal basis for V. Those were our two orthonormal bases for V. If P is a transition matrix from one of them to the other one, so if our transition matrix is a transition matrix from one orthonormal basis to another one, that would be a matrix where if you took a vector in that vector space relative to one basis, this relative to your new base, the coordinates of your vector relative to your new base is equal to the transition matrix from your old basis to new basis times the coordinates of that vector relative to the basis. So it would be a matrix P where this equation holds. That would be P. The conclusion is that this P, this transition matrix, is orthogonal, is an orthogonal matrix, is a matrix whose inverse is, whose transpose is equal to its inverse. That's the conclusion of theorem 7.1.5. That this transition matrix is an orthogonal matrix, is a matrix whose transpose is equal to its inverse. That's the conclusion. Right? Then P is an orthogonal matrix. Conclusion. Okay? So that's theorem 7.1.5. So it's dependent on a lot of vocabulary that we learned, a lot of concepts we learned about before. If you understand all the things from before, this is a little bit extra, but not too bad. If earlier things don't make sense, this will be extremely complicated to understand. Okay, so let's keep going. Okay, so my suggestion is you need to study earlier stuff in order for all of this to make sense. Okay, so next, let's say we have the x-axis and y-axis. Then okay, so let's say we have our original coordinate axes, x and y axes, right? And then let's consider the core axes x prime and y prime, which is just a rotation of theta degrees about the origin counterclockwise. So I'm just taking the original core axes and I'm rotating them about the origin theta degrees counterclockwise. Counterclockwise, right, is this direction. So I'm going in that direction counterclockwise and rotating it about the origin. I'm fixing the origin, I'm just moving everything theta degrees counterclockwise. Then my new axes I'm going to call x prime and y prime. X prime is x after it's moved, y prime is y after it's moved. Okay? And so now I'm going to just relate the coordinates relative to the old core axes. I'm going to relate those coordinates to the coordinates relative to my new core axes. And so x prime is equal to x cosine theta plus y sine theta. and y prime is equal to negative x sine theta plus y cosine theta. And so these are just the new coordinates after the original point is rotate theta degrees counterclockwise. And so these two equations are called the rotation equations for R2. What that means, if you take a point x comma y, and if you rotate it, I'm just going to write it down, rotate it theta degrees counterclockwise about the origin, right, is the point 0, 0, right? So if I take the point x, y, and rotate it theta degrees counterclockwise about the origin, then I will have transformed the point x comma y to the point x prime comma y prime. And x prime and y prime are determined by x, y, and theta. And you plug x, y, and theta into these two equations and you get x prime, y prime, the new coordinates. Okay, so it's pretty simple. You just plug them in. You can even memorize the equations and then you've now found where that point goes. Okay, but that's for R2, right? So this is for R2. And so we need other equations in order to deal with R3. So let's say we have the x-axis, y-axis, and z-axis in R3. And then we're going to rotate it by theta degrees counterclockwise. And we're going to do it in the xy plane. And so when we do that, we're going to get new coordinates x prime and y prime. Okay? And so x prime and y prime are perpendicular, because the original ones were. And I rotated this by theta degrees. And so both axes will be rotated by theta degrees, and the result will be those two new coordinates are still perpendicular. Okay. But now the z coordinate is going to stay exactly the same. And so I'm going to rotate the x and y coordinates theta degrees counterclockwise, and I'll keep the z coordinate exactly the same. And so this new equation I'm going to represent using a matrix equation. And so the new coordinates are going to be x prime, y prime, z prime, respectively. And you're going to get that by multiplying this matrix okay, we're going to get the coordinates of our new point by multiplying this matrix by the original coordinates x, y, z. And so the result, when you multiply this matrix by this matrix, you'll get a 3 by 1 matrix. And the components of that 3 by 1 matrix will tell you the coordinates x prime, y prime, z prime of your new point, which you might label as x prime. Okay? And these are the rotation equations for R3. Okay, even without understanding the equations, if you just plug in the old coordinates and multiply with this matrix on the left, you get the new coordinates. Okay, and so that's the end of 7.1. Orthogonal diagonalization. Okay, so 7.2 orthogonal diagonalization. Definition 1 for 7.2. If A and B are square, then B is orthogonally similar to A if there is an orthogonal matrix P such that B equals P transpose AP. Okay, so if A and B are square matrices, then B is orthogonally similar to A if there's an orthogonal matrix P such that B equals P transpose AP. Okay. So if B is orthogonally similar to A, that implies that A is orthogonally similar to B. So saying B is orthogonally similar to A implies that A is orthogonally similar to B. Okay, and so you can see that because if P is orthogonal, its inverse is also orthogonal, and so there's a way, if you have the equation B equals P transpose AP, there would be a way to find another orthogonal matrix, which I'm just going to say P prime, such that A is equal to P prime T A. A is equal to P prime T B P prime B. Sorry. Then there would be a way to say A is equal to P prime T B P prime, where P prime is also orthogonal. All right. So being able to write this equation means you could also write this one. And so if B is orthogonally similar to A, then A is orthogonally similar to B. Okay. And so when one matrix is orthogonally similar to the other, we can just say that they are both orthogonally similar. Okay. Okay. So the conclusion of that is just that we say A and B are orthogonally similar. Okay. Either they're orthogonally similar or they're not orthogonally similar. We won't say one is orthogonally similar to the other. Okay. Okay, and as a note, an important note in this section, in 7.2, orthogonal means orthogonal with respect to the Euclidean inner product with respect to the Euclidean inner product on Rn. Okay, so orthogonal means orthogonal with respect to Euclidean inner product on Rn. So the Euclidean inner product function, right, determines whether or not a matrix is orthogonal. And so, the inner product you use will determine whether or not it's orthogonal. And so that means that I'm going to just specify that we're always using the Euclidean inner product on Rn in section 7.2. Okay, in this section. Okay, let's keep going. Okay. Theorem 7.2.1. Okay, if A is n by n, so if A is an n by n matrix with real entries, then the following are equivalent. I'll write the word then so it's clear this how the if then statement is working. Okay. So if A is an n by n matrix with real entries, then the following are equivalent. Statement A, A is orthogonally diagonalizable. B, A has n orthonormal has an orthonormal set of n eigenvectors. And C, statement C, is A is symmetric. And just a reminder what symmetry means. Symmetry means A is symmetric means that A transpose is equal to A. Right? Okay, C is the easiest thing to understand, and so I just wrote next to it so you can get 1 out of 3. Making sense. Okay, so theorem 7.2.1 says that if A is an n by n matrix with real entries, then the following are equivalent. Those 3 statements have the same truth value. If one of them is true, all 3 of them are true. If one of them is false, all 3 of them are false. Okay, statement C is asymmetric, and that means that the matrix A is a matrix such that A transpose is equal to A. Okay, if you switch the rows to columns or the columns to rows, you end up with the exact same matrix. That's statement A. Okay, and that's either true or false, but not both. Statement B is A has an orthonormal set of n eigenvectors, and so A is an orthonormal set of n eigenvectors, right? An eigenvector V is a vector such that AV is equal to lambda V for some constant lambda, right? That would be an eigenvector V. And this is for some scalar lambda, which was fixed as a constant. For some constant scalar lambda, AV equals lambda V. Then V, little v, would be an eigenvector of A. And so what statement B is saying is that A has an orthonormal set of n eigenvectors, meaning you can find n vectors with this property where for some scalar lambda, AV is equal to lambda V. You can find n of those V's, where if you can form a set of those nV's, V1 to Vn, you can form a set. They form a set that's an orthonormal set, meaning the length of all these V's is 1, and it's an orthogonal set, where if you take any 2 of them, their inner product is 0. Again, with respect to the Euclidean inner product, like I said in this section, the inner product function is always the Euclidean inner product. Okay, so always assuming Euclidean inner product. If you take the inner product of any 2 of these vectors, it's 0. That's what makes this an orthogonal set. And the length of all these vectors is 1. And that's what makes it, and in addition to being orthogonal, that's what makes an orthonormal set. And these n vectors are n eigenvectors, are n vectors V such that AV equals lambda V for some scalar lambda. That's what statement B is saying. Okay? Okay, that's B. So that's either true or false, not both. It has the same truth value as the other 2 statements. Statement A is orthogonally diagonalizable. And so, oh, okay, this is why I was looking. Let me put this definition right here. The definition here is if A is orthogonally similar to some diagonal matrix, P transpose AP is equal to D, where D is the diagonal matrix, we say A is orthogonally diagonalizable. And P orthogonally diagonalizes A. So that explains statement A. Okay? The definition of an orthogonally diagonalizable matrix. Okay, if A is orthogonally similar to some diagonal matrix, meaning that for some orthogonal matrix P, D is equal to P transpose AP, where D is a diagonal matrix. That would mean that the matrices A and D are orthogonally similar. Okay? Then we would say that A is orthogonally diagonalizable. Okay? A is orthogonally similar to some diagonal matrix D. Before I define 2 matrices being orthogonally similar, but none of them have to be diagonal matrices. And so if you have a matrix A, and you can show it's orthogonally similar to a matrix D, where D is a diagonal matrix, then A is orthogonally diagonalizable. That's the definition of a matrix being orthogonally diagonalizable. It's orthogonally similar to a diagonal matrix. Okay? And so either it is or isn't orthogonally diagonalizable. If it is, that statement's true. And if it's false, then if it's not orthogonally diagonalizable, then statement A is false. Okay, so all three of those statements are all true or all false. That's the meaning behind the following are all equivalent. The following are equivalent. Okay? So that's a lot to take in. So this theorem is saying those three statements have the same truth value. And that's the definition of statement A. Okay, and I reminded you the definition of statement C. And so A and C are coming directly from those two definitions that I wrote right here on the board, right? This definition is explaining A, and I wrote right next to it the definition for C. Okay, and you just have to think about what B is saying, and I wrote that down a little bit earlier in the video, a few minutes ago. Okay, and so that's theorem 7.2.1. So theorem 7.2.2. If A is a symmetric matrix, so if A is a symmetric matrix with real entries, then statement A, the eigenvalues of A are all real numbers. And B, the eigenvectors from different eigenspaces are orthogonal. Okay, so theorem 7.2.2. If A is a symmetric matrix, meaning A transpose is equal to A, so A is a symmetric matrix with real entries. The entries are not complex. In section 5.3, we studied complex matrices where the entries could be complex numbers. Here, the entries are only real numbers. Okay, so A is symmetric with real entries. Then these two statements are true. Okay. So now this theorem, we're going back and forth between the following are equivalent and not that. These two statements are just both true. That's the conclusion of this theorem. So statement A is true, the conclusion, that the eigenvalues of A are all real numbers. And so if you find the eigenvalues of A, if you find the characteristic equation of A, and you solve for the eigenvalues that satisfy the characteristic equation, those eigenvalues are all real numbers, right? The characteristic equation is the equation determinant of lambda I minus A is equal to 0. That equation is you're given, let's say, A, and you have to find the values, the constants lambda that satisfy the equation, the determinant of lambda I minus A equals 0. Those values of lambda are the eigenvalues of that matrix A. And so statement little a is saying that all the lambda that satisfy that equation are real numbers. There is no constant lambda that satisfies this equation that's a complex number or any other kind of number other than a real number. Okay, and so that's statement A. Statement B, little b, eigenvectors from different eigenspaces are orthogonal. Okay, so when you find the eigenvalues, so you have your characteristic equation. You find all the values of lambda that satisfy that equation. Okay, and for each value of lambda that satisfies this equation, for that lambda, so you choose one of the lambdas that satisfy that equation, and then you get the linear system lambda naught I minus A x equals 0. Okay, so if lambda naught, so the assumption is that lambda naught is an eigenvalue. And so if lambda naught is an eigenvalue, then what happens is that implies that the general solution to that equation, the set of all x values that satisfy that equation, right, that's the eigenspace corresponding to lambda naught. Right, so the general solution of this, of that equation, is the eigenspace corresponding to lambda naught. I'm just reminding you some things, right? So again, you have this equation, the determinant of lambda I minus a equals 0. All the values of all the constants lambda that satisfy that equation are eigenvalues of a. So that's how you find the eigenvalues of a. Take one of those eigenvalues of a, call it lambda naught. Lambda naught, assuming lambda naught is an eigenvalue of a, then when you have this equation, lambda naught I minus a times x equals 0, then now this is a fixed, we know what this is now, and a we were given. So the unknown here is x in this equation. The unknowns have changed. Before it was lambda, now it's x. The unknown here is x. All the vectors x that satisfy this equation, that's the general solution of that equation. And the general solution of that equation, all the vectors x that satisfy that equation for a fixed lambda naught, which is an eigenvalue of a, all those solutions is what's called the eigenspace corresponding to lambda naught. Okay? So now, that's what an eigenspace corresponding to an eigenvalue of a matrix is. All the solutions to this equation for some fixed lambda naught, which is an eigenvalue of a. Now, if you take two different eigenvalues, let's say lambda naught, lambda 1 are eigenvalues of a, and I'm going to say they're not equal. So we want different eigenspaces. So if we take two, we have to take two different eigenvalues in order to have two different eigenspaces. If you take the same eigenvalue, then it will have the exact same corresponding eigenspace, right? So we have two different eigenvalues of a. And if you start with that assumption, then if you look at the eigenspaces corresponding to each of those vectors, and so let me call E1 the eigenspace corresponding to lambda 1. Sorry, E naught is the eigenspace corresponding to lambda naught, and E1 is the eigenspace corresponding to lambda 1. So if you have those two eigenspaces corresponding to those two different eigenvalues, then what happens is if you take a vector little v1 in capital E naught, little v naught in capital E naught, and little v1 in capital E1, meaning I take a vector from one eigenspace and I take another vector from the other eigenspace, then they're orthogonal, meaning if I take the inner product of those two vectors, it's equal to 0. That's what two vectors being orthogonal means, right? Again, this inner product is the Euclidean inner product on Rn, because that's the assumption of this entire section 7.2. Okay, so if we have two different eigenvalues of a, that means that we have two different eigenspaces corresponding. If we have an eigenspace corresponding to each different eigenvalue of a, let's call E naught and E1. And so if I take a vector one from each eigenspace, v naught and v1 and E naught and E1 respectively, and I take the inner product of those two vectors at 0. That's the conclusion of B. That's what B is saying. Eigenvectors from different eigenspaces are orthogonal. These two vectors are eigenvectors. V naught is an eigenvector and V1 is an eigenvector, because they're vectors in eigenspaces corresponding to an eigenvalue of the matrix. So these two vectors are eigenvectors, and when you take the inner product of them at 0. That's what statement B is saying. Okay? Okay. You got it. Procedure for orthogonally diagonalizing. So procedure for orthogonally diagonalizing an n by n symmetric matrix. Okay, so procedure for orthogonally diagonalizing an n by n symmetric matrix. Step 1. Find a basis for each eigenspace of A. Okay, so step 1 is find a basis for each eigenspace of A. This is the procedure for orthogonally diagonalizing an n by n symmetric matrix. Step 1, find a basis for each eigenspace of A. Step 2, Right, okay, so I talked on the very last board, I gave the whole explanation of what the eigenspace of a matrix is, right? You find the eigenvalues of that matrix, and for each eigenvalue, there is a corresponding eigenspace for that eigenvalue, right? Okay, so you find the eigenvalues of A, and then you find the corresponding eigenspaces of those eigenvalues. Now, each of those eigenspaces is a vector space, and so it has a basis. And so you're finding a basis for each eigenspace. That's step one. Step two, apply the Gram-Schmidt process. To each of the bases, to each of these bases, to obtain an orthogonal basis. For each eigenspace. So step two, apply the Gram-Schmidt process to each of these bases to obtain an orthogonal basis for each eigenspace, okay? So when you have each eigenspace and you find a basis for each eigenspace, because each eigenspace is a vector space with bases, right? So you find a basis for each eigenspace, okay? The Gram-Schmidt process is a way to take any basis of a vector space and transform it into an orthonormal basis for the same vector space. Okay, and so for each eigenspace, we found a basis, and so we can just transform that basis into an orthonormal basis for that eigenspace. Okay, and that's what the Gram-Schmidt process again does. It takes a basis, it transforms a basis to an orthonormal basis. And so once you understand what the Gram-Schmidt process does, step two is just simple, because you're just taking a basis and you're transforming it to an orthonormal basis using that process. And that's step two. Okay, so that's nothing new. Step three, form the matrix P whose columns are the vectors constructed in step two. Okay, so form the matrix P whose columns are the vectors constructed in step two. Okay, so in step two, you now found an orthonormal basis for each eigenspace, and so for each orthonormal basis, you'll have vectors for each orthonormal basis. Take those vectors in each orthonormal basis, and in any order, make them the columns of a matrix you'll call P. Okay, step two, you get orthonormal bases, and each one has vectors in it. So just take all those vectors and all the bases you found in step two, and just make them the columns of a matrix you're going to call P. That's the next step. Okay, and that's easy. Step three is very simple. Okay, and so now that matrix P, this matrix P that you created in the step, this matrix P orthogonally diagonalizes A. Okay, and that's from the definition, right? So saying P orthogonally diagonalizes A means that there's a diagonal matrix D such that D is equal to P transpose AP. That's what it means for P to orthogonally diagonalize A. And so we found a matrix P that orthogonally diagonalizes an n by n symmetric matrix A. Okay. But we can go further than that in this conclusion. This matrix P orthogonally diagonalizes A, and the eigenvalues on the diagonal of D, which is equal to P transpose AP, because P orthogonally diagonalizes A, so diagonal matrix D, will be in the same order as the corresponding eigenvectors in P. Okay. So, when we formed the matrix P, we chose the vectors from step 2, right? We made the columns of P vectors. We use all the vectors in the bases from step 2. We use those vectors to form all the columns of P. The order in which we chose the vectors didn't matter, right? We could have made, you can make the columns of P, you can make the columns any order you want. But when you do that, once you form P, the order in which you chose those columns will determine the order of the eigenvalues on the diagonal of the diagonal matrix D. And so the D that you get will be different depending on the order of the vectors you chose as the column vectors that form the matrix P. Okay? Okay, so for instance, if in the first column of matrix D, you chose a particular V1, a particular vector in one of your bases for one of your eigenspaces, V1. Well, if the first column of P was V1 and the second one was V2 to Vn, then when you got a D at the end, the diagonal matrix D, the top left entry, the entry on the first row, or the first column, whichever you want to think of it, that entry on the diagonal, that first one, will have to be the eigenvalue in which the vector V1 was in the eigenspace of. So if V1 is the eigenspace corresponding to the eigenvalue lambda 1, then the eigenvalue lambda 1 will be the one in the first row or first column of D. If V2, the second column of matrix P, was an eigenvector you chose from lambda 2, which was one of the eigenvalues of A, then the second diagonal entry of D would be lambda 2. And so the vectors you chose as column vectors of matrix P, they're all eigenvectors in corresponding eigenspaces. And so those eigenspaces, right, are from an eigenvalue for each of them, not necessarily distinct, right? Some of those vectors are from the same eigenspace. And so you could have a repeat of the eigenvalues on the diagonal. And so if 3 of the vectors that form the columns of P are from the same eigenspace, then there'll be 3 of the same eigenvalue on the diagonal of D. If that makes sense, okay? And so step 3 is just saying the conclusion would be that we found a way to orthogonally diagonalize our symmetric matrix A. And it specifies what D is, what the D is in this equation. Okay? It tells you where the eigenvalues go on the main diagonal that forms the matrix, diagonal matrix D. Okay, so that's a 3-step procedure. So you can take each step one at a time. Okay? So understand each step separately, and then you can do all 3, and then to complete this process. Okay? Go. So that's the end of 7.2. So now 8.1. 8.1 is entitled General Linear Transformations. Okay, so definition 1. If T from V to W is a mapping from vector space V to a vector space W, then T is a linear transformation. Then T is a linear transformation from V to W. If for all vectors U and V in vector space capital V and scalars K, we have these two properties. One, that T of Ku is equal to K times T of U. That's called the homogeneity property. And second one, which is called the additive property, is T of U plus V is equal to T of U plus T of V. Okay, if V equals W, T is called a linear operator. T is a linear operator. T is a linear operator on the, in addition to all this other stuff, on the vector space capital V. Okay, so definition 1 and 8.1 on general linear transformations. If T from V to W is a mapping from vector space V to a vector space W, then T is a linear transformation from V to W if, for all vectors U and V and capital V and scalars K, T of Ku equals K times T of U, and T of U plus V equals T of U plus T of V. This is called the homogeneity property, that's called the additive property. And if V equals W, in addition to all of that, T is called a linear operator on the vector space V. Okay? So normally we defined what is meant by a linear transformation from V to W, right? But if W is the same as V, instead of saying linear transformation from V to V, we could just say it's a linear operator on V. And so that's all that additional statement says. It's just a shorter, more succinct way of saying a linear transformation from V to V. A linear operator on V, instead of saying a linear transformation from V to V. Okay? And that's all. It doesn't say anything else other than that, this last part. Okay? And so here we have the definition of a linear transformation from V to W. A function which these two properties hold for. Okay. So you want to keep this equation in mind and this equation in mind. Those two equations you want to know. Okay, you'll need them to either know, and either to assume a function is a linear transformation or to prove something is one. Okay. So you need to know those two equations. If V1 to V sub R are in vector space capital V, and K1 to K sub R are scalars, I'm using the little r here because I'm talking about R of them, and so I'm going from 1 to R so I can talk about an arbitrary R many vectors and scalars. Then T of K1 V1 plus K2 V2 plus dot 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 plus KR VR is equal to K1 T of V1 plus K2 T of V2 plus dot 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 plus K sub R T of V sub R. And that is statement 1 in this section. Okay, so if you take T of that linear transformation, take T of this linear combination, you're going to get this, where you can just move the constants out of the T's and you can separate the term. You can separate them into R terms like this. So you'll get this plus dot 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 plus that. It'll be a sum of products looking like that. Okay, and so this is directly from the two properties in the definition of a linear transformation from V to W. The fact that I can now separate this T of a sum into a sum of T's, so I could say T of this is T of K1V1 plus T of K2V2 plus dot 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 plus T of KRVR, and then for each of those T's I could move the constant out and get that. Okay. Next is theorem 8.1.1. That's if T is from V to W is a linear transformation, those two equations hold from the last board, then, so if T from V to W is a linear transformation, then two statements hold. T of 0 is equal to 0, and B, T of U minus V is equal to T of U minus T of V. And this is for all U and V in vector space capital V. Okay, T of 0 equals 0, and T of U minus V equals T of U minus T of V. That's theorem 8.1.1 with the assumption that T is a linear transformation from V to W. Okay, that's our assumption. Logically, that's our assumption, and our conclusion is that equation A holds and equation B holds. So now we have another, that's another theorem. Let's keep going. Fact. Every matrix transformation T sub A from Rn to Rm, where Rn equals V, Rm is equal to W, and the zero transformation which is T of V is equal to 0 for all little v and capital V, is a linear transformation. Okay, so every matrix transformation and zero transformation is a linear transformation. Okay, so well, any of these guys and this guy, they're linear transformations. Okay, so if you have a function that's left multiplication by matrix A, or if you have a zero transformation that maps every vector to 0, those are all linear transformations. Those are all functions that satisfy the two equations, T of KV equals KT of V, and T of U plus V equals T of U plus T of V. Those two equations, those hold for either of those. The matrix transformations, like that, and the zero transformation. Right? The conclusion is that those functions are linear transformations. Functions that satisfy those two equations in the definition of a linear transformation. Okay, so that's the conclusion. They're linear transformations. That's a fact. Another fact is that the identity operator on V I of V is equal to V for all little v and capital V is a linear transformation. Okay, so the identity operator on V, I of V equals V for all little v and capital V, is a linear transformation. Okay, the identity operator on V is just a function that maps a vector to itself. Okay, and that is a linear transformation. It satisfies the two equations in the definition of a linear transformation, right? So I of K of V equals K times I of V, and I of U plus V equals I of U plus I of V. Okay, that's another fact. Another fact is that T from V to V given by t of x is equal to k x is a linear operator on V. Oh, so actually that's the assumption, okay? So the assumption is that, but then if 0 is less than k less than 1 in this definition of t of x equals kx, if that k there, the constant k, is strictly between 0 and 1, then t, that function t, is a contraction of V with factor k. Okay? So it's called a contraction of V with factor k. Contraction of V because we're multiplying x by maybe from a number between 0 and 1, so it could be 1/2 x. So in a sense we're making it smaller. And if k, instead of being strictly between 0 and 1, let's say k is greater than 1, then t is a dilation of V with factor k. Okay, so when your eyes dilate, your pupils get bigger, and so when k is greater than 1, meaning t of x is equal to kx, where k is a scalar greater than 1, t is called a dilation of V. And so you could talk about the norm of t of x. Well, the norm of t of x is the absolute value of k times the norm of x. And if k is greater than 1, the norm of t of x will be greater than the norm of x. It'll be k times greater. And so you'll be making the norm of t of x bigger. And in that sense, you'll call it a dilation. The norm is getting bigger. Okay? Good. Okay, so that's another fact. So now we have 3 more facts here on this board. 3 more things that we know. Okay. Good. Contraction, smaller, dilation, bigger. Theorem 8.1.2. Okay, so theorem 8.1.2. Let t be from V to W. Be a linear transformation. Where capital V if S is V1 to V sub n is a basis for V, then the image of any vector, little v in capital V, can be expressed as T of V, which is equal to C1 T of V1 plus C2 T of V2 plus dot 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 plus Cn T of Vn. This is statement 3. It's not part of the expression, I'm just labeling that equation as 3, where C1 to C sub n are the coefficients required to express little v as a linear combination of the vectors in basis capital S. Okay, so this is theorem 8.1.2. Let T from V to W be a linear transformation where V is finite dimensional. If S is this set is a basis for V, then the image of any vector little v and capital V can be expressed as T of V is equal to that expression. C1t of V1 plus C2t of V2 plus dot 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 plus Cnt of Vn, where the C's are the coefficients required to express V as a linear combination of the vectors in basis S. Okay, so what does this mean? Where the C1 to Cn are the coefficients required to express V as a linear combination of the vectors in basis S. What that means is that we can write V as equal to C1 V1 plus C2 V2 plus dot 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 plus Cn Vn. Okay? That's what that squiggly underlined part of this theorem says. Is saying, where C1 to Cn are the coefficients required to express V as a linear combination of the vectors in basis S. This is basis S. It consists of the vectors V1 to Vn. And so if you can express V as a linear combination of the vectors in basis S, then we can write V equal to C1 V1 plus C2 V2 plus dot 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 plus C of Vn. And the C's here, the coefficients next to each of the vectors in basis S for V, those C's will be the same C's here. So I'm not changing the C values. When you write V as a linear combination of the vectors in basis S, you get C values here in your linear combination. Those C's, you then put them here. And now you can see that TV is equal to that expression using the C's from this equation. Okay? So that's the conclusion, is that the image of any vector little v and capital V under T, or T of V, can be expressed, or you can say T of V is equal to that. That's the conclusion. And so I'm explaining the C's in this equation are the C's in that equation. Okay. Example 10. Consider the basis S, which is equal to V1, V2, V3. Consider the basis S for R3, where V1 is equal to 1, 1, 1. V2 is equal to 1, 1, 0, and V3 is equal to 1, 0, 0. Now consider the basis S for R3, where those three are the vectors in basis S for R3. Okay. Let T be from R3 to R2 be the linear transformation for which T of V1 equals 1, 0. T of V2 is equal to 2, negative 1. And T of V3 is equal to 4, 3. Find T of x1, x2, x3, and use it to find T of 2, negative 3, 5. Okay, so that's the basis for R3. Those three are the vectors. Let T be from R3 to R2 be the linear transformation for which T of V1 is this, T of V2 is that, and T of V3 is that. Find T of x1, x2, x3, and use it to find T of 2, negative 3, 5. Okay. So I'm going to use another mark. So solution. Solution is going to be blue. Okay. So first off, let's talk about the vector x1, x2, x3, which we're going to input into T. So that vector x1, x2, x3, let's write it as a linear combination of the vectors in basis S. Here's our basis S for R3, consisting of the vectors v1, v2, and v3. And so we're going to express this vector x1, x2, x3 as a linear combination of those three vectors in the basis. So we get c1 times 1, 1, 1, plus c2 times 1, 1, 0, plus c3 times 1, 0, 0. Now I'm writing this vector as a linear combination of the basis vectors in basis S for R3. Okay? And so you would just find a corresponding linear system to this equation, and you would find the general solution to that corresponding linear system, and you would solve for the C values here. And so from earlier problems, you solve for those values of C, and so I'll just tell you what those C's will be. C1 is going to be equal to x sub 3. C2 is going to be equal to x2 minus x3. And C3 is going to be equal to x1 minus x2. Okay? So this three tuple, x1, x2, x3, we're thinking of a fixed vector in R3. Because that means these are fixed values. x1, x2, x3 are not unknowns. They're just letters. We're using them to denote fixed values. Okay? And so we can treat these fixed values just like we would a number. So if there was a 1 there, the arithmetic I would do on the number 1, I could do with x1. So x1, x2, and x3 are fixed values. And so when I solve for C1, C2, and C3, I end up getting expressions involving x1, x2, and x3. And that's all right, because saying C1 is equal to x3 means C1 is equal to the fixed number that's in the third component of my vector there. And so C1 is still equal to a fixed number, even though it's equal to x3. It's not equal to a variable x3, it's equal to a fixed number x3. C2 is equal to the difference of two fixed numbers, x2 minus x3. And C3 is equal to the difference of the two fixed numbers, x1, x2. So it's x1 minus x2. Okay, so now I found a solution to this equation. From the earlier theorem, we showed that T of V, or T of x1, x2, x3, can be expressed as C1, T of V1, plus C2, T of V2, plus C3, T of V3, where the C's are the same as before. So when I found the C's that satisfy this equation, I'm finding the C's that I can plug in here. So T of x1, x2, x3 is equal to x3 times T of v1 plus x2 minus x3 times T of v2 plus x1 minus x2 times T of v3. And so now I've expressed T of x1, x2, x3 like this. Okay? But here we know what T of v1 is. T of v1 is 1, 0. And so T of v1 here is going to be 1, 0. So this is going to equal x sub 3 times 1, 0 plus x2 minus x3 times T of v2. Well, what is T of v2? T of v2 is equal to 2, negative 1. So I'm going to substitute T of v2 here for 2, negative 1. Okay? This parentheses is just for the constant x2 minus x3. This parentheses has a comma in it, and so that's an ordered pair. So this is a number times an ordered pair here. And then plus x1 minus x2 times T of v3. And T of v3 is equal to 4, 3. And so I would plug in 4, 3 here. And so now, if I just multiply and add this up, I should get 1, 2 tuple here. And so the 2 tuple you get after you do all that arithmetic is 4x1 minus 2x2 minus x3. I'm going to have to write the equal sign over here. This is going to be equal to the 2 tuple 4x1 minus 2x2 minus x3, comma, 3x1 minus 4x2 plus x3. Okay, so t of x1, x2, x3 is equal to 4x1 minus 2x2 minus x3, comma, 3x1 minus 4x2 plus x3. And so now we found a t of x1, comma, x2, and comma, x3. T of this is equal to that two-tuple. That's the first component, that's the second component. And so where it says find t of x1, x2, x3, check, and use it to find t of this. So to find t of that, you just plug in those numbers. And so t of this is equal to, remember, this is equal to, when you plug in 2 for x1, negative 3 for x2, and 5 for x3, and you do that here also, you end up, after a bunch of arithmetic, you get 9, comma, 23. Okay? And so t of 2, comma, negative 3, comma, 5, you just plug them in, those values in here, and you get 9, comma, 23. And that's the answer for the second part. And so we're done with that also. Let's keep going. Check real quick something. Okay, good. Looking good. So next, this fact. So if d from v to w is the function that maps f to f prime, meaning it maps the function f to its derivative, or d of f is equal to f prime of x, that function is a linear transformation. Okay, so we can say that all the functions defined on the real line is a vector space. And so that v, that capital V vector space, capital V, you can think of it as the vector space of functions defined on the real line. And, it's the differentiable functions defined on the real line. Okay, functions that are differentiable on the real line. And so that's our vector space V. And so if you d maps a function f to f prime, that's a linear transformation. You can see that because d of k times f is equal to the derivative of the function kf. Well, that's just equal to k times f prime. That's k times d of f. And so the homogeneity property holds. And then if you take d of f plus g, where f and g are two functions in the vector space capital V, they're two functions that are differentiable on the real line, then this is equal to the derivative of f plus g. But then the derivative of f plus g is the derivative of f plus the derivative of g. That's equal to d of f plus d of g. And so I just showed that d of f plus g equals d of f plus d of g. And so this function g also has the linear property. Has the additive property. And so this function d has a homogeneity property, additive property, has the two equations in the definition of a linear transformation. And so this d is a linear transformation. It's definition 2. So t from v to w is a linear transformation. So t from v to w is a linear transformation. Then the set of vectors in capital V that t maps into 0 is the kernel of t. denoted by KAR of T. The set of all vectors in W that are mapped to by some vector in capital V under T is called the range of T. Is the range of T. Denoted by capital R of T. Okay, so here's definition 2. If T from V to W is a linear transformation, then the set of vectors in capital V that T maps into 0 is the kernel of T, denoted by KR of T. The set of all vectors in W that are mapped to by some vector in capital V under T is the range of T, denoted by R of T. Okay? Okay, and so if you think of all the vectors that T maps to 0, it's the kernel of T. And if you think of all the vectors in W, that is the image of some vector in capital V under T, that's the range of T. Okay, so let me say that in this picture. So if you have this picture here, and this is V and this is W. Then if you have A, ignoring trying to think of, you know, let me just use the 0 vector, 0. That way it's like, makes sense. So then let's say I have 0 in there, okay? So T, let's say T maps A, B, and C to 0, and then nothing maps to 1. The kernel of T would be A, B, C, because those would be everything in V that maps to 0. So the set A, B, C is the kernel of T. And if I talk about the image of T, if I talk the range of T, I would say the set containing only 0, because 0 is the only thing in W that is mapped to by something in T. Is mapped to by something in V under T. Nothing maps to 1, and so the range of T would only be 0. Okay, so here the range of T would be the 0 set, and here the kernel of T would be the set A, B, C. Okay, so that's illustrating in a simple way the idea of this definition of the range and kernel of a linear transformation T. Okay, so your two definitions, the kernel of T and the range of T for a linear transformation T. This is an example of that, of those two definitions, that picture. Okay. Good. I'm going to try to use green now. Example 13. If T sub A from Rn to Rm is multiplication, which means left multiplication, is multiplication by m by n matrix capital A, then the kernel of T sub A is the null space of A. And the range of T sub A is the column space of A. Okay, so this is example 13. So this is just saying these things. Okay, so T sub A from Rn to Rm is multiplication by m by n A. Then the first thing it says is then the kernel of T sub A is the null space of A. What that means is, well, if you look at the kernel of T sub A, okay, so looking at the kernel of T sub A, that's the notation for the kernel of T sub A. What that means, T sub A is left multiplication by A, right? And the kernel of left multiplication by A is just all the vectors x that t sub A maps to 0, or all vectors x such that ax equals 0. That's the kernel of t sub A, all the solutions x to ax equals 0. Well, all the solutions x to ax equals 0 is also called the null space of A. And so the kernel of t sub A is equal to the null space of A because they're both the solutions of x to the equations ax equals 0. Right, both the kernel of t sub A and the null space of A, they're both the solutions x to the equation ax equals 0. So they're both equal to each other. Okay, now the range of t sub A, denoted by r of t sub A, well, the range of t sub A is just t sub A is left multiplication by A. And so the range of t sub A would just be all the possible values of ax, all the possible values of left multiplication by A. And so here, the range of t sub A is just the set of all possible values, the set of all values b that have a solution to the equation ax equals b. Okay? So x is an unknown, but we can say that for each b I put here, for that particular b, either there's some x such that ax equals b, or there are no x values such that ax equals b. And so the range of t sub A is all the possible b's I could put here, such that for each of them, there's some x such that ax equals b. That's the range of t sub A. Okay? But the range of t sub A is all possible values of b such that ax equals b has at least one solution. Well, that's the range of t sub A is one way to say that. But then if I were to talk about the column space of A, the column space of A is the set of all linear combinations of the column vectors of A. And so if my matrix A is split up into columns, C1, C2, Cn. Now I'm not using the same notation as before. Before the C's were constants. Here C's are column vectors. So C is for column now, not constant. So the C1 to Cn here, only in this equation right now. In the past it was different things, depending where you're looking. Here they're column vectors. So first column, second column to nth column. So the column space of A is the span of the set containing those n vectors, or the set of all linear combinations of the columns of A, the vectors C1 to Cn. Well, the set of all linear combinations of C1 to Cn would just be if I took A here and I multiplied it by x on the right side. Well, x is a vector with n components because this is an m by n matrix A, and so I'm multiplying it by n by 1 matrix here, and I'm getting x1 to xn. Well, so if I take an arbitrary x here, and I think if I wanted to think of all linear combinations of the columns of A, I could equivalently just think of, I could use any constants I wanted to multiply each column vector by, and then I would just add up the products of numbers times each constant. I could equivalently say, I could write that exact same thing as just choosing n constants, x1 to xn, and multiplying that matrix by this one. And so that this matrix times this one would just be another way to represent a linear combination of the column vectors of A. Because this matrix times this matrix would be x1 c1 plus x2 c2 plus plus xn cn. And so, if I want to know the set of all linear combinations of the column vectors of A, I could just say it's the set of all values of this matrix times this matrix. Okay? And so if I have the set of all possible values of this matrix times this matrix, if I just call this equal to B, then saying the set of all B values would be the same as saying the set of all possible values of this matrix times this matrix. So the column space of A is the same as the set of all matrices B, such as there's at least one solution to Ax equals B. And so the range of T sub A and the column space of A are both talking about the exact same set. The set of all B's such that Ax equals B has at least one solution. Okay, and so since both of these things represent the same set, they're equal to each other. And so that's what example 13 concludes, that the kernel T sub A is equal to the null space of A, and the range of T sub A is equal to the column space of A. So for one more time, these two things are all the set of all possible x's in this equation, and these two things are all the set of all possible b's in that equation. And so these two are equal to each other, and those two are equal to each other. That's example 13. Okay, so that's example 13. Now, theorem 8.1.3. If t from V to W is a linear transformation, then A, the kernel of T is a subspace of V. B, the range of T is a subspace of W. Okay? So if T from V to W is a linear transformation, then A, the kernel of T is a subspace of V, and B, the range of T is a subspace of W, right? So when you think of the kernel of T, you're thinking of vectors in its domain V that get mapped to 0. And so the kernel of T is definitely a subset of V. But the conclusion is that it's also a subspace of V. It's a vector space, which is a subspace of V, okay? And B, the range of T is a subspace of W. Well, the range of T is a set of vectors in W, the codomain of T. And so we already know the range of T is a subset of W, but B tells us more. It tells us in addition to being a subset of W, it's also a subspace of W. It's a vector space in its own right. Okay, and so you can prove A and B by just showing, proving the theorem to prove that something is a subspace of a vector space. You could just show that it's closed under addition and scalar multiplication for both of them. And then for both A and B, you're proving that it's a subspace of V and W respectively. So for instance, in A, the kernel of T is a subspace of V, right? So if you take V1 and V2 in the kernel of T, so V1 and V2 belong to the kernel of T. If I assume that, then that would mean that T of V1 is equal to 0 and T of V2 is equal to 0, right? Because both V1 and V2 are in the kernel of T, they're both vectors that T maps to 0. But then, knowing those two equations, I could then conclude that T of V1 plus V2, actually I'm going to write this here so I have more room. T of V1 plus V2 is equal to, so the kernel of T, so T of V1 plus V2 is equal to T of V1 plus T of V2. This is from the fact that T is a linear transformation. This is because T is a linear transformation. And so because T is a linear transformation, it has the additive property of a function, meaning T of V1 plus T V2 equals T of V1 plus T of V2. But I know that each of these things is 0, so this is 0 plus 0, which equals 0. So I just showed that T of V1 plus V2 is equal to 0. And that means that V1 plus V2 is in the kernel of T, because V1 plus V2 is a vector that T maps to 0, because T of V1 plus V2 is equal to 0. And so if you have two vectors in the kernel of T, then the sum is also in the kernel of T. That means that the kernel of T is closed under addition. And then if V1 is in the kernel of T and also K is a scalar, okay, then that implies that T of V1 is equal to 0, K is a scalar, and that implies that T of KV1 is equal to K times T of V1. This is again because T is a linear transformation. Same reason, okay? And this has to do with this. So this equals this because T is a linear transformation. But then T of V1 is 0, so this is K times 0, which equals 0. So I just showed that T of KV1 is equal to 0, and that implies that KV1 is in the kernel of T. And so assuming that V1 is in the kernel of T and K is a scalar, then K times V1 is in the kernel of T. And so this is the homogeneity property of a linear transformation. And so this T has both the additive property and the homogeneity property. The two equations in the definition of a linear transformation hold for this T. Oh, sorry, not linear transformation, sorry. I showed that this T is closed under addition and scalar multiplication. And so that T then is a subspace. So then that means that, the kernel of T is closed under addition and scalar multiplication. So the kernel of T is a subspace of V. Okay? The kernel of T is already a subset of V showing the kernel T is closed under addition and scalar multiplication means it's a subspace of V by theorem, by an earlier theorem. So that's how you show that the kernel T is a subspace of V, and very similarly, you could show the range of T is a subspace of W by showing that the range of T is closed under addition and scalar multiplication. And so by theorem, that means that the range of T, which is already a subset of W, is also a subspace of W. Okay. Definition. Let T from V to W be a linear transformation. Okay, so a T from V to W is a linear transformation. If the range of T is finite dimensional, then its dimension is called so let T from V to W be a linear transformation. If the range of T is finite dimensional, then its dimension is called the rank of T. Okay, also, and if the kernel T is if the kernel T is finite dimensional, then its dimension is called the nullity of T. Okay, so the rank of T is denoted by rank in parentheses T, and the nullity of T by nullity of T. Okay, so the rank of T is denoted by rank parentheses T, and the nullity of T is by nullity parentheses T. Just that's the notation for the rank and nullity of T. Okay, so if the range of T is finite dimensional, then its dimension is called the rank of T. And if the kernel T is finite dimensional, then its dimension is called the nullity of T, right? So the rank and nullity, the range, we showed the range of T and the kernel of T are both subspaces, right? So in the last board we showed they're subspaces. And so as subspaces, they're vector spaces, right? So the range of T and the kernel of T are both vector spaces. And every vector space has a dimension, right? It's the number of vectors in any basis for that vector space, right? And so if a basis for each of those vector spaces consists of exactly finitely many vectors, it's finite dimensional. Okay? And so the dimensions of the range of T is the rank of T, and the dimension of the kernel of T is the nullity of T. Okay. Let's keep going. That's a definition of the rank and nullity of a linear transformation T. Okay. Theorem 8.1.4. If T from V to W is a linear transformation, from a finite dimensional vector space V, to a vector space W, then the range of T is finite dimensional. And the rank of T plus the nullity of T is equal to the dimension of V. It's a V. And this is statement 7 in section 8.1. Okay? So if T from V to W is a linear transformation from a finite dimensional vector space V to a vector space W, and the range of T is finite dimensional, and the rank of T plus the nullity of T is equal to the dimension of V. Okay, so essentially, with a bunch of conditions, the rank of T plus nullity of T is equal to the dimension of V. Okay. Note. If T sub A from Rn to Rm, A is m by n, is multiplication by A, again meaning left multiplication. The kernel of T sub A is the null space of A. And the range of T sub A is the column space of A. Thus, we talked about this before, thus, by theorem 8.1.4, the one right above it right there, we have the rank of T sub A plus the nullity of T sub A is equal to n. We get this equation. Okay, so T sub A from R to Rm, where A is an m by n matrix, is multiplication by A. The kernel of T sub A is the null space of A. The range of T sub A is the column space of A. Thus, by this theorem, we have already T is a matrix transformation. This T is left multiplication by A, multiplication by A. Every matrix transformation is a linear transformation. So this T sub A is a linear transformation. So by theorem 8.1.4, for a linear transformation, we have its rank, the rank of T sub A, plus the nullity of T sub A is equal to the dimension of V. Well, what is the dimension of V? It's the dimension of the domain of T sub A. The dimension of R to the n is n. And so since T sub A as a matrix transformation is also a linear transformation, we can apply this equation in theorem 8.1.4 to this situation and get the rank of this transformation, the rank of T sub A plus the nullity of T sub A is equal to the dimension of Rn, which is n. So rank of T sub A plus nullity of T sub A is equal to n. Okay, and so that's the end of 8.1. And so let's keep going. Eight point two. Compositions and inverse transformations. So 8.2, compositions and inverse transformations. Definition 1. If T from V to W is a linear transformation, from vector spaces V to W, then t is 1 to 1 if t maps distinct vectors in capital V into distinct vectors in capital W. So if t from V to W is linear transformation from vector spaces V to W, then t is 1 to 1 if t maps distinct vectors in V into distinct vectors in W. Okay, that's the definition of 1 to 1 linear transformation. Definition 2. Second definition. If t from V to W is a linear transformation, I'm going to abbreviate it as LIN. So if t from V to W is a linear transformation, I'm going to write trans period for transformation. So t from V to W is a linear transformation from vector spaces. And V and W are vector spaces. So t from V to W is a linear transformation from vector space V to vector space W. Then t is onto if every vector in W is the image of at least one vector in capital V. So if t from V to W is a linear transformation from vector space V to vector space W, then t is onto if every vector in W is the image of at least one vector in capital V. That's the meaning of an onto linear transformation. Okay, so we have the definition here of a 1 to 1 linear transformation, the definition of an onto linear transformation. So theorem 8.2.1. So t from V to W is a linear transformation. Then the following statements are equivalent. Then the following are equivalent. A, t is 1 to 1. B, the kernel of t is the 0 set. Okay, so if t is linear transformation from vector space V to vector space W, then the following are equivalent. These two statements have the same truth value. That's the conclusion. Statement A, t is 1 to 1. Statement B, the kernel of t is the 0 set. That means that the only vector that t maps to 0 is 0. Okay, so t of V is equal to 0 only when V is equal to 0. That's statement B. So those two statements are equivalent. Okay, and so you could prove that theorem, and you would show that those two statements are equivalent. Theorem 8.2.2. If V and W are finite dimensional vector spaces, so I'm going to write finite dimensional, meaning finite dimensional vector spaces, or finite dimensional with the same dimension. So V and W are finite dimensional vector spaces with the same dimension, and if T from V to W is a linear transformation, then the following statements are equivalent. Then TFAE, the following statements are equivalent. The following are equivalent. Statement A, T is 1 to 1. B, the kernel of T, I feel like this is a waste of time now that I wrote both these. Kernel of T is equal to the 0 set. And C, oh no, okay, no, this is fine. and CT is onto. And that means, i.e., the range of T is equal to W. The set of all images under of T is equal to the codomain W. Every vector in W is mapped to by something in V under T. Okay, so the conclusion is that these three statements, A, B, and C, are all have the same truth value, or all equivalent. They're either all three of them are true, or all three of them are false. Okay, so T is 1 to 1. That's from the definition of T. This is the same statement as that one. The only vector that T maps to 0 is 0. And CT is onto is from the definition. And so all these three things are true or false if V and W are finite dimensional vector spaces, and that finite dimension is the same. So V has the same dimension as W as a finite dimensional vector spaces. Okay, and T is a linear transformation. Okay, so that's theorem 8.2.2. Okay, example 1. If T sub A is from Rn to Rm is multiplication by n A, then T sub A is not 1 to 1. I'm going to abbreviate 1 to 1 as 1-1. So it's not 1 to 1 if m is less than n, and not onto if n is less than m. So if T sub A from Rn to Rm is multiplication by n matrix A, then T sub A is not 1 to 1 if m is less than n, and it's not onto if n is less than m. Okay? Also, when m equals n, from theorem 4.10.2 in your book, T sub A is both 1 to 1 and onto. If and only if A is invertible. Okay? So when m is equal to n, from theorem 4.10.2, T sub A here, this function here, is both 1 to 1 and onto if and only if A is invertible. That means that when m equals n, the statement that T sub A is both 1 to 1 and onto is equivalent, has the same truth value as A is invertible. And so when m equals n, if A is invertible, then T sub A is both 1 to 1 and onto. And when m equals n, if A is not invertible, then T sub A is not both 1 to 1 and onto. Meaning it's either not 1 to 1 or not onto, or both not 1 to 1 and not onto. Okay, so those two statements have the same truth value if, when, and m equals n. Okay, and so so depending on the relationship of m and n, you reach these three different conclusions. Okay? The first one is if m is less than n, the second one if m is greater than n, and the third one is if m equals n. Okay, good. Example 2. Okay, so look at example 1 when you're studying this section. T1, let's say T1 is from P sub 3 to R4. And T sub 2 is from M sub 2 to R4. And they're defined by T1 of A plus BX plus CX squared plus DX cubed is equal to A comma B comma C comma D. And T sub 2 of the matrix A, B, C, D is equal to A comma B comma C comma D. Okay, so you have those two transformations, T1 and T2. T1 goes from the set of all polynomials degree at most 3 to the set of all 4 tuples. T2 goes from the set of all 2 by 2 matrices with real coefficients to R4, the set of all 4 tuples. Okay,
And so T1 is defined by T1 of this polynomial is equal to the 4 tuple, which are just the coefficients A, B, C, and D in that order. And T sub 2 of the 2 by 2 matrix here is just the 4 tuple where you take as entries, take as components the entries in the 2 by 2 matrix in that order. Okay? Now, you could ask the question, what is the kernel of each of these T's? What is the kernel of T sub 1 and what is the kernel of T sub 2? Well, the kernel of T sub 1, is the set of all vectors in P sub 3 that get mapped to 0 from this definition of T sub 1. Well, so we're asking, what are all the vectors in P sub 3 that get mapped to 0? Vectors in P sub 3 are polynomials of degree at most 3. Right? Vectors are just elements in the set V in your vector space. Right? Vectors are not and tuples like you normally think of them in physics or other math problems. Right? Vectors here are just elements of the set that's part of your team of members that make up your vector space. Right? So here, in this vector space, a vector is a polynomial, and a vector in this vector space is a 4 tuple. Okay, so the image under T1 of a vector of P3, right, is this. And so we want to know, well, what polynomials does T1 map to the 0 vector in R4? The 0 vector in R4 is just the 4 tuple of all zeros. 0, 0, 0, 0. And so it's obvious to see that the only polynomial that gets mapped to 0, 0, 0, 0 is just 0 plus 0x plus 0x squared plus 0x cubed. That's a 0 polynomial. And so the 0 polynomial you could denote as just 0. So the kernel of T sub 1 is just the 0 set. Only the 0 polynomial gets mapped to the 0, 4 tuple under T1. And the kernel of T sub 2 is just the set of all vectors in M sub 2, 2 that T sub 2 maps to the 0, 4 tuple in R4. And so the only 2 by 2 matrix that will map to the 0 vector in R4, the only matrix, M2 by 2 matrix that will map to 0, 0, 0, 0, 0 is the 0 matrix, 0, 0, 0, 0. And so the kernel of T sub 2 is also the 0 vector. Alright, and this might be weird because when I'm thinking of vectors in P sub 3, when I'm thinking of polynomial vectors that are polynomials or vectors that are matrices, I'm still using the notation 0 when talking about an element of a vector space containing polynomials or a vector space containing matrices. But that's fine because the 0 symbol in linear algebra takes on more uses than the 0 used to take. 0 used to only be a number. Right? Now, a 0 in linear algebra can also be, depending on the context, depending on where you're reading that 0, we could also have 0 meaning the 0 vector in a vector space. And so the 0 polynomial is the 0 vector in P sub 3, and the 0 matrix is a 0 vector in M sub 2, 2. And so by writing 0 here, I really mean here a 0 polynomial and here a 0 matrix, and that's fine. And so now the kernel of both of T1 and T2 is just the 0 set. And so that implies that from our previous theorem, that both T1 and T2 are 1-to-1. And onto. So T1 and T2 are both 1-to-1 and onto. And that's because by theorem 8.2.2, we said that if you had a linear transformation T from V to W, right, where V and W are finite dimensional and the same finite dimension, then 3 statements were equivalent. T is 1-to-1, the kernel of T is the 0 set, and T is onto. So by showing that the kernel of T1 is equal to the 0 set, that means it's equivalent to saying that T1 is 1-to-1 and equivalent to saying T1 is onto it. So T1 is both 1-to-1 and onto. Right? But the condition of this is theorem 8.2.2 earlier in this lesson. Theorem 8.2.2, we have to know that our 2 vector spaces were finite dimensional of the same dimension. T1, P3 is dimension 4, and R4 has dimension 4. And so these 2 are finite dimensional of the same dimension. Here, T2, M sub 2, 2 is finite dimension of dimension 4, and R4 is finite dimensional of dimension 4. And so these 2 are both finite dimensional vector spaces of the same dimension. And so for both T1 and T2, they both meet the conditions of theorem 8.2.2. And so when we show that both of them have the kernel of the 0 set, that means they both are also 1-to-1 and onto. And that is by theorem 8.2.2. So this is by theorem 8.2.2. And so we now show that T1 and T2 are both 1-to-1 non-2. And that's example 2. Okay? And so if you can show the kernel of a transformation is the of a linear transformation is the 0 set, then by theorem 8.2.2, right, if both V and W are finite dimensional vector spaces of the same dimension, you could then use that theorem to show that it's 1-to-1 non-2. Okay, so that's example 2. So you want to look at these. Both these examples are very good to study for section 8.2. So I would focus on example 1 and 2 when studying and understanding 8.2. What's on this board, these two examples. Okay, definition 3. Definition 3. So if T1 is from U to V and T2 is from V to W, and they are linear transformations, right? So we're just giving them a name by saying linear transformations. It meets all the conditions of linear transformation. We know we're assuming a lot of things about T1 and T2 already, right? So T1 and T2 are linear transformations. Then the composition of T2 with T1 denoted by T2 composed with T1 is the function defined by T2 composed with T1 of U is equal to T2 of T1 of U. And this I'm going to do as statement 1 in this section 8.2. And that is defined by that, where U is a vector in capital U, vector space capital U. Okay, so in definition 3, this is the definition of the composition of T2 with T1. Okay, T2 composed with T1 of U is equal to T2 of T1 of U. And so you're performing these operations from right to left. So first you find T1 of U, and then the result of T1 of U, you plug that into T2. Because you take T2 of that. And so you get, is that if you have a vector space U, and a vector little u and capital U, and you have a vector space V here, and you have a vector space W there, T1 of U, let's say T1 of U is here. And so U goes to T1 of U under T1. And then T2 would take T1 of U, and T2 would map T1 of U to T2 of T1 of U, and that would be in vector space W. But then another way to take U and map it to T1 of U under T1, and then map T1 of U to T2 of T1 of U under T2, would just be take U and go directly to there, to the endpoint, T2 of T1 of U, by taking U of T2 composed with T1. And so this is a picture that is illustrating what T2 composed with T1 is. Okay, so T2 composed with T1 of a vector little u and capital U is the function that maps little u to T2 of T1 of U. And what that means is what T2 composed with T1 does is it maps U to T1 of U, and then T1 of U to T2 of T1 of U. Okay, so that's illustrating the composition of T2 with T1. And this is figure 8.2.2 in section 8.2. This is figure 8.2.2. Okay, so that's definition 3. Composition of T2 with T1. Okay, so let's keep going. Okay, theorem 8.2.3. If T1 is from U to V, T2 is from V to W as linear transformations, then T2 composed with T1, which is a function from U to W, is also a linear transformation. What that means is a composition of linear transformations is another linear transformation. Compositions of linear transformations are linear transformations. That's what this theorem says. Okay? That's theorem 8.2.3. Example 7. Okay? If T1 from V to W is a linear operator, and if I from V to V is the identity operator, then for all vectors little v in capital V, we have that T composed with I of V is equal to T of I of V, which is T of V, and I composed with T of V is I of T of V, which is equal to T of V. And that implies T composed with I is equal to T, and I composed with T is equal to T. And that's 2. Those two equations. This and that is numbered as 2. Okay, so T1 is a linear operator, and if I from V to V is the identity operator. Sorry, this is T from V not to W, V to V, because it's a linear operator, but W could just equal V. But T1 from V to V is a linear operator, and if I from V to V is the identity operator, then for a little v in capital V, we have the T composed with I of V. It is T of I of V by the definition of a composition of two linear transformations. But then I of V is the identity operator, so I of V is V, and so this is T of V. Here I of T of V, I composed with T of V is I of T of V by the definition of composition of linear transformations. But then T of V, I of T of V, I is the identity operator, so I of something is that something. So I of T of V is equal to T of V. And so what we just showed is that T composed with I of V is equal to T of V. So T composed with I takes any vector V and maps it to T of V. And so what T composed with I is, it's T. T composed with I is equal to T. T composed with I takes a vector V and maps it to T of V. That's the same thing T does. And so the same, T composed with I is T. I composed with T takes a vector V and maps it to T of V. And so I composed with T is also T. Okay, and so T composed with I is T, and I composed with T is equal to T. That's the conclusion, 2 conclusions of example 7. Okay, let's keep going. Let T1 be from U to V, T2 from V to W, and T3 from W to Y be linear transformations. Okay, so linear, the T1, T2, and T3 are linear transformations with range R of t. And oh no, the linear transformations. Sorry, I just forgot. So T1, T2, and T3 are linear transformations. Then T3 composed with T2 composed with T1 is equal to T3 composed with T2 composed with T1 of V, which is equal to T3 of T2 of T1 of V. And that's statement 3. Okay, and so statement 3 is just saying that the function T3 composed with T2 composed with T1 is a function that maps V to T3 of T2 of T1 of V. Okay, next, if T from V to W is a one-to-one linear transformation with range R of T, and if little w is any vector in capital R of T, then the inverse of T denoted so T from V to W is a one-to-one linear transformation with range R of T, and if W is any vector in R of T, then the inverse of T, denoted by T inverse, defined on R of T, maps W back into V, where T of V equals W. Okay, so let's look at figure 8.2.4 in the book. And so this figure tells us that if you have your vector space V, and you have your vector space R of T, R of V, the range of a vector space is also a vector space. So the range of T, the range of a linear transformation is also a vector space. So we're going to V to R of T. So we take a vector little v and capital V, T will map that V to W, which is T of V, but then that W, T inverse, will map that W. So the arrow is going in the opposite direction, but it's still just a function that has an input W and output V. So T inverse is a function whose input is W, which is T of V, and whose output is V. Okay, and so what this function is illustrated, what this picture, figure 8.2.4 in the book, what figure 8.2.4 is illustrating is that how the inverse of T looks. Okay, so here T is a linear transformation with range R of T, but it's also one-to-one. We're assuming that T is one-to-one at the beginning. We need to assume T is one-to-one. If T is not one-to-one, it doesn't have an inverse. Okay, so T is one-to-one, and so if W is any vector in the range of T, then first off, as W is being a vector in a range of T, means it's the image of something in capital V. That means that T of V is equal to W for some little v in capital V. Okay, so since W is in the range of T, I can take some v, little v in capital V, and T will map that little v to W. What that means is that T inverse is defined as being the function that will take that W in the range of T and it will map it to the vector V such that T of V is equal to W. It'll just undo what T did. T inverse is like undoing what T did. So if T is a map that maps V to W, T inverse will map W back to V. That's what T inverse does. It's like doing the opposite of what T did. Right? If you add 3, the opposite would be to subtract 3. If a function maps v to w, the opposite would be to map w to v. And so if you added 3, you could then subtract 3 and get right back where you started. If you took a linear transformation and mapped v to w, you could then map w to v and get back where you started. And so T inverse is just the thing that you could do after T to get back where you started. That's T inverse. So we're defining T inverse. We're defining what that idea is, what it means to undo what T did. So if T of V equals W, then T inverse of W equals V. And that's how we're defining T inverse, right? And again, T has to be 1-to-1, and R of T is the range of T. And so the domain of T inverse is the range of T. We're only inputting things into T inverse that has an image. That is the image of something under T, okay? If this vector was not mapped to by something in capital V, then I could not go backwards in a sense, right? I could not go back to the vector that maps to it. And so the range, so the set of all inputs of T inverse is only the set of all things that are mapped to by something in capital V under the function T. Okay, so the set of inputs of T inverse is only the range of T, not more than that. Okay? And so here we're just defining what the inverse of T is and illustrating it by that picture. Okay. Keep going. So we're almost done. A little bit more to go. Okay, now I'm going to try the black marker again. So we have T inverse, and T inverse is from the range of T to V. And if that is a linear transformation, oh, sorry, so T inverse from the range of T to V is a linear transformation, okay? So when you find T inverse, it's a linear transformation. And T inverse of T of V is equal to V. And T of T inverse of W is equal to W. And so this is equation 4 in this section. And this is statement or equation 5. Okay? And so illustrating 4, if you have a vector space capital V, and then you have your vector space capital W, and little v is in capital V, and T maps little v here, right? And so it'll map it to little w in capital W. But then T inverse will take that W and map it back to V. And so T of V, right, which is W, then if I take T inverse after it, I'll get back V. And so T inverse of T of V is V. And so that's illustrated by that picture. This second equation, 5, is illustrated by this picture. So again, if we have V here, and we have vector space V here, and vector space W here, and we take little v in capital V, if we take little w in capital W, and we map T inverse, and T inverse will map it to V, right? But here, so here we're talking about the range of T here. So here we're going to take a W in the range of T, and T inverse is going to map it to V, but then T of that V is going to be W. Okay, here W is T of V, right? So we're going to choose a W in the range of T. That means that it's W is equal to T of V for some little v in capital V. Then T inverse of W is equal to V. Then T of that V is W. And so what that's saying is that if you start with W, and you take T inverse of it, T inverse of W is V. But then T of that V is W. And so this is illustrating how T of T inverse of W is W. And that's equation 5. So this is equation illustrated by this picture, and that equation is illustrated by that picture. Okay, so theorem 8.2.4. Okay, so if T1 is from U to V, and T2 is from V to W, or 1-to-1 linear transformations, then T2 composed with T1 is 1 to 1, and B, T2 composed with T1 inverse is equal to T1 inverse composed with T2 inverse. So theorem 8.2.4 says that if T1 is from U to V and T2 is from V to W are 1 to 1 linear transformations, then T2 composed with T1 is 1 to 1. Sorry, and T2 composed with T1 inverse is equal to T1 inverse composed with T2 inverse. Okay, good. Okay. Okay, so T3 composed with T2 composed with T1 inverse is equal to T1 inverse composed with T2 inverse composed with T3 inverse. So just like the previous example, we're just reversing the order. When we take a composition of linear transformations that are 1 to 1 and we take its inverse, it's just the composition of their inverses in reverse order. So here we have T3 composed with T2 composed with T1 inverse. Now we're going to do T1 inverse composed with T2 inverse composed with T3 inverse. We reverse the order of the T's. Okay, and also T sub CBA inverse is equal to T sub A inverse times T sub B inverse times T sub C inverse. Okay, and that follows directly from the previous equation. Okay, so T sub CBA is the transformation of left multiplication by the matrix CBA. So T sub CBA is the transformation CBAX, left multiplication of vector x by the matrix product C times B times A, CBA times x. Now if I take the inverse of that, okay, the inverse of this so I guess I won't use that. The inverse of this left multiplication by CBA, well, T sub CBA is left multiplication by, right here, left multiplication by CBA. But this is the same as starting with x, then left multiplying by A, then left multiplying by B, and then left multiplying by C. So left multiplication by CBA is the same as first left multiplication by A, then left multiplication by B, then left multiplication by C. And so that means that T sub CBA is equal to, first if you do T sub A, then you do T sub B, then you do T sub C. Because you're going from right to left when you do composition. So left multiplication by CBA is left multiplication by A, then left multiplication by B, then left multiplication by C. And so T sub CBA inverse would equal the composition of the inverses of these things in reverse order. And so it would be T sub A inverse composed with T sub B inverse composed with T sub C inverse. I'm just taking the inverse of this, which is the inverse of this composition, but it would be the composition of inverses in reverse order. So T sub A inverse composed with T sub C inverse. But then we're still not done because this is T sub A inverse times T sub B inverse times T sub Z inverse. And so the inverse of T sub A is the inverse of left multiplication by A, and that's left multiplication by A inverse. If you left multiply by A, to undo left multiplication by A, you can multiply by A inverse and you would get x. And so the inverse of left multiplication by A is left multiplication by A inverse. So T sub A inverse is T sub A inverse. And so T sub A inverse is T sub A inverse, and that would be then composed with T sub B. Similar idea. If T sub A inverse is T sub A inverse, if T sub A inverse is T sub A inverse, very similarly, T sub B inverse is T sub B inverse, and T sub C inverse is T sub C inverse. And so the composition of these things is that. So now we just showed, you can abbreviate the composition symbol by just writing them next to each other. So this is T sub A inverse, T sub B inverse, T sub C inverse. So I just showed that T sub CBA inverse is equal to T sub A inverse times T sub B inverse times T sub C inverse. And so now I just proved this equation right here, using the previous equation there. Okay. Okay, and so this is equation 8. The upper box here, this is 8, and this is 0.9 in 8.2. Okay, and so that's the end of 8.2. Let me just quickly... Good, okay. So that's the end of 8.2, and so there's just one section left, 8.3. And then we're done. Isomorphism, definition 1. Okay, so definition 1 is a linear transformation So a linear transformation, T from V to W, that is both one-to-one and onto, is an isomorphism. And W is isomorphic to V. Okay, so this definition is very important in mathematics, definition of an isomorphism, and so if you go further into abstract algebra, you'll be dealing with isomorphisms, and they also turn up in a lot of other advanced courses. So the definition is a linear transformation from T from V to W that is both one-to-one and onto is an isomorphism. Okay, this is the definition of isomorphism. And so this is kind of condensed because we're already assuming that T is a linear transformation. Right? And so T being a linear transformation means that T of KV is equal to K times T of V. That's the homogeneity property. And T of U plus V is equal to T of U plus T of V for all vectors u and little v in vector space capital V, right? Where T is a linear transformation. Okay. So these two equations hold already as T is a linear transformation. But then we're also including now that it's one-to-one. T is one-to-one. And T is onto. So really, even though it looks like I'm saying a linear transformation T that is both one-to-one and onto is an isomorphism. But there's not really two conditions because we're already assuming it's a linear transformation. So you might say there's four conditions for a function to be a linear, for a function to be an isomorphism. One, that T of KV equals K times T of V. Two, that T of U plus V equals T of U plus T of V. These two combined are the same as saying T is a linear transformation. Okay, so by showing that a function is a linear transformation and one-to-one and onto, you could also say it in a more fundamental way that this equation holds, and that T is one-to-one and T is onto. Okay, so saying T is an isomorphism is just a function where all four of these properties hold. Okay, so if you show your function satisfies all four of these things, if all four of these things are true for your function T, then that means that T is an isomorphism. Okay, so T is from V to W. And so if you can show that T is an isomorphism, all four of these things hold, then you could say that W is isomorphic to V. And so what's interesting is that if you can find a function T from V to W where these four things hold, not only can you say something about T, that T is an isomorphism, right? That doesn't only tell you something important about T, it actually tells you something important about the things that T maps. So it tells you something about the relationship between the domain and codomain of T. T being an isomorphism, we say means that its domain V and codomain W are isomorphic. Okay? And in mathematics, by finding an isomorphism between two spaces, you could actually by knowing that relationship between two spaces, you could actually use that to prove or find answers to mathematical questions. Just studying the relationship between those two spaces. Okay, but anyway, isomorphism is something where all four of these things are true for that function. That's an isomorphism. And so if T from V to W is an isomorphism, then W is isomorphic to V. Okay? Okay. Okay, also, T from V to W, if that's an isomorphism, that implies that T inverse from W to V is an isomorphism. Okay? You need your function to be 1-to-1 in order to have an inverse. But T is an isomorphism, which means it's 1-to-1 already. That's one of the conditions in order for a function to be an isomorphism. So we know T is 1-to-1 because it's an isomorphism, which means it has an inverse function. And so what we can say about that inverse function is if T is isomorphic, if T is an isomorphism, then T inverse is also an isomorphism. Okay? And so because T being an isomorphism implies T inverse is an isomorphism, then we can say, thus we say, B and W are isomorphic. To each other. And that T is an isomorphism between V and W. Okay? So, definition 1a, linear transformation T from V to W that is both 1-to-1 and onto is an isomorphism, and W is isomorphic to it. Okay, that's the definition, right? But here, okay, so here I'm saying T from V to W is an isomorphism, implies T inverse from W to V is an isomorphism. Okay? And so, when T from V to W is an isomorphism, by this definition, we say that W is isomorphic to V. But if W is isomorphic to V, then we know T inverse tells us that V is isomorphic to W. And so if W is isomorphic to V, then V is isomorphic to W. And so that means if either space is isomorphic to the other one, we could just reverse the order. So each space is isomorphic to the other one. And so we never have to say that one space is isomorphic to the other. We can just say that the two are isomorphic to each other. Okay? So thus we say V and W are isomorphic to each other. We're just isomorphic. And that T is an isomorphism between V and W. Because whenever we find an isomorphism from V to W, we can also find an isomorphism from W to V. Okay? So we just say T is isomorphism between V and W. Because both, when one space is isomorphic to the other is also isomorphic to the first. Okay. Okay, so we have that written there. Okay. Next. Theorem 8.3.1. Every real n-dimensional vector space is isomorphic to Rn. Okay? So every real n-dimensional vector space is isomorphic to Rn. What that means is that if V is our n-dimensional vector space, then we can find an isomorphism F that will map V to Rn. Okay? And that isomorphism, what that isomorphism will do is it'll map F of V to its coordinates relative to some, you could say that we could find an isomorphism where the isomorphism F from an n-dimensional vector space V to Rn, you could define that F as being F of V is equal to the coordinates of V relative to S, where S is a basis for V. Okay, so if you have a basis for V, then F of V could equal the coordinates of V relative to S, and that would be an isomorphism from an n-dimensional vector space V to Rn, and that would show that V and Rn are isomorphic. Because we found an isomorphism F between them. F of V is equal to coordinates of V relative to S, where S is a basis for capital vector space capital V. Okay, actually, so that's the next theorem. Okay, so theorem 8.3.2. If S is V1 to Vn is a basis for a vector space capital V, then the coordinate map that maps U to the coordinates of U relative to S, so I'm just going to write the T there, is an isomorphism between V and Rn. And so to prove that this theorem, the conclusion of this theorem is that the coordinate map T there is an isomorphism between V and Rn. And so if this theorem is true, we're now showing that every n-dimensional V, it's n-dimensional because S is a basis for V and it has n vectors, V1 to Vn. So hidden in here is the fact that V is n-dimensional. And so we're showing that this map, this coordinate map, is an isomorphism between V and Rn. That would prove this theorem, theorem 8.3.1, that every n-dimensional vector space is isomorphic to Rn. This would be an isomorphism between them, which would prove those two spaces isomorphic. Okay, and so you could show this is an isomorphism by showing you have a linear transformation that's both 1-to-1 and onto. Okay, so if you show this T is a linear transformation that's both 1-to-1 and onto, then that T would be an isomorphism. Okay, linear transformation that's both 1-to-1 and onto, that would be an isomorphism. And show that about this T, and you have an isomorphism between them. That would prove this theorem, which would also prove that theorem. Okay, so now we're almost done. Very close. So example 1. A naught plus a1x plus a2x squared plus dot 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 plus a sub n minus 1 x to the n minus 1. Let's say T maps that to a naught comma a1 comma dot 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 comma a2 comma dot 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 comma a sub n minus 1. Defines the natural isomorphism between p sub n minus 1 and Rn. Okay, so p sub n minus 1 and Rn are isomorphic. And so there is an isomorphism between p sub n minus 1 and Rn. And so one specific isomorphism between them, you can have more than one isomorphism between two spaces, two fixed spaces. One isomorphism is this one, and it's called the natural isomorphism between p sub n minus 1 and Rn. It's the natural function that you would probably the most natural function you would choose to show that those two spaces are isomorphic. It's the easiest isomorphism. It's the easiest isomorphism to think of between p sub n minus 1 and Rn. The one that where you take this n minus 1, when you take a polynomial of degree n minus 1, you would just take the coefficients starting with this one to that one, and they would make them respectively the coordinates of this n tuple here. So here, this coefficient would be the first component, the next coefficient would be the second component, the next coefficient would be the third component, and so the last coefficient of the polynomial here would be the last component of that n tuple there. This is an n tuple because you're going from a naught to a n minus 1. And so because the subscripts are going from 0 to n minus 1, that means there's n of them. There are not n minus 1 subscripts. Even though the last one says a sub n minus 1, there's actually n components in this vector because we're going from 0 to n minus 1. 1 to n minus 1 would be n minus 1, But 0 to n minus 1 is 1 more than n minus 1, which is n. Okay, so that's an n tuple. Okay, so example 2. Example 2 is if we take the 2 by 2 matrix A, B, C, D, and T maps that to the 4 tuple A, comma, B, comma, C, comma, D, then this defines the natural isomorphism between M, capital M, sub 2, 2, and R4. But I think more generally, I would like to, because this is a 2 by 2 matrix and that's a 4 tuple. More generally, so this is the natural isomorphism between M sub 2, 2, and R4. So I also want to talk about the natural isomorphism between M sub Mn and R to the M times N. And so that matrix, that transformation, involves a little bit more writing. That transformation will be A sub 1, 1, A sub 1, 2, dot, 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 A sub 1, N, A sub 1, N. This would be A sub 2, 1, A sub 2, 2, dot, 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 A sub 2, N. And then this would be dot, 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 A sub M1, dot, 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 A sub M2, dot, 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 A sub Mn. So this would be the general representation of an M by N. So this is capital M sub Mn. This is a general expression for an M by N matrix. Okay. So okay, so capital M. So this is just an M by N matrix here. M rows, N columns. And so if you take that matrix and you map it to all of these components, so you start with A11, A12, dot, 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 A1N. Then you go A21, dot, 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 A2N. Then you go dot, dot, dot. You continue that pattern up until you have the last row. AM1, dot, 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 AMN. Basically, you just take the entries in this matrix, you go from here to here, then here to here, then here to here. You have a total of M times N entries. And so you're mapping this matrix to this M times N tuple. So it would be M times N tuple. That would mean there would be N times N components to this vector. And this would be the natural, this T would be the natural isomorphism between capital M sub Mn and R to the M times N. And so this T would be the natural isomorphism between capital M sub Mn and R to the M times N. Okay? And then, okay, and then there's one more problem, and then it's completely done. Okay, so A here is this matrix. Let's say we have this matrix here, and we have, okay, so here's A. This is example 12 in 8.3. So we have this A. If we find the determinant of A, we're finding the determinant of this matrix. Okay, and so we're finding the determinant of that matrix. Okay, so when we find the determinant of this matrix, okay, then when you find the determinant of that matrix, you could take the cofactor expansion along the second row. So this would be minus 2 times the determinant of that submatrix, and you would get negative 2 times 0 minus 1 is negative 1. Oh wait, sorry. And this would be, that would be the submatrix. Okay, so it would be 1 minus, and that'd be 1 minus 1, which is 0. So you get negative 2 times 0, which is 0. And so this implies that the determinant of A is 0. but that implies that A is not invertible. When the determinant of a matrix is 0, that means it's not invertible. But when A is not invertible, that implies T sub A is not both 1-to-1 and onto. If T sub A was both 1-to-1 and onto, then it would be invertible. But because A is not invertible, that means T sub A is not both 1-to-1 and onto. And this is by example 1 in this lesson. Earlier in 8.3 there was an example 1. And so you should go back, not 8.3, 8.2. Example 1 in 8.2. I'm going to put the circle around. Example 1 in 8.2. So you want to look at that. Okay. Example 1, 8.2. So A is not invertible, therefore T sub A is not both 1-to-1 and onto. Okay. And so then that implies that T sub A is not an isomorphism. And we're done. Okay, so in this example, we want to show, by showing T sub A is not an isomorphism, we are done with the problem. Okay, here's A. We found the determinant of A is 0. Determinant of A is 0 implies that A is not invertible by the equivalence theorem. That implies that T sub A is not both 1-to-1 and onto by example 1 in section 8.2. That implies that T sub A is not an isomorphism. That's by the definition of isomorphism. Isomorphism is a linear transformation that's both 1-to-1 and onto. And so since T sub A is not both 1-to-1 and onto, it's not an isomorphism by definition. And we're done with example 12. Okay, so that's all the material for both the rest of this lesson, chapter 8, and for the entire semester, for the entire course. Okay, and so good luck on the test, and I will post up solutions to problems from the study sheet. Okay, bye.